Good morning, good afternoon, and good evening to all who are tuning into our presentation today. Our topic is how to minimize material imbalance using Sigmafine's material balance and data reconciliation models. Let's take a quick look at the agenda for our presentation. We start with a brief introduction, followed by what is material balance. Then we look at how Sigmafine's reconciliation models can be used to minimize material imbalance. Then we have a deep dive into a refined products terminal case study, followed by a description of how measurements can be audited. We then wrap up with some Q&A. Hi, I'm Sheetal Francis, Project Manager at Shuro International. Shuro International is an Abu Dhabi, UAE-based system integrator providing business process automation solutions to our customers that helps them embrace digital transformation as one of their key strategic initiatives. For this, we use technology from market leaders and industry experts like the PI system that acts as a real-time data infrastructure and historian. We also make use of Sigmafine tools and solutions that offers a system of balances and checks to ensure that its users are provided with data that's coherent, trustable, and usable. Apart from this, Shuro International's portfolio of solutions also includes GIS implementations, learning management systems, predictive analytic solutions, and electromechanical solutions. So let us dive straight into our topic, material balance. So what exactly is material balance? The law of conservation of mass states that mass can neither be created nor destroyed. In terms of material balance, we can say that raw materials into a particular process should be equal to the sum of the products of that process plus the waste products plus stored products and losses. Losses are often unidentified and unknown. So if this equation is not true, then it means there is a material imbalance. Simply put, the mass of a specific material in the raw materials or inputs to a process should be equal to the mass of that specific material in the products of that process plus the mass of that specific material in the waste products and losses. Sigmafine material balance models helps to ensure that these losses, which are unidentified, gets identified and detected so that we can come up with a solution to reduce these imbalances. In a typical refinery, if we were to measure the overall imbalance, the ideal scenario should be that the overall imbalance is less than 10%. But in refineries around us, we often notice that this imbalance is between the range of 5 to 7%. But using Sigmafine's data reconciliation and material balance models, we can help our users reduce this imbalance further to below 5%. You also see a gouge here, which is an indicator of model solvability. This really gives an indication of the extent of poor values in the model. You see a dark green part, which denotes solvable, a light green part, which denotes redundant, and a red part that denotes non-solvable. Using Sigmafine's material balance models, we ensure that the model is in a redundant state. This means that even if one value were to fail, there is another set of value which will help to produce reconciled data. Sigmafine also uses indicators, such as the one we see here, a measurement correction indicator, which is really a test. The indicator T1 is obtained by taking the difference between reconciled value and raw value and dividing this by the tolerance. Using this indicator for the different meters of the process, it's possible to rank these meters. By looking at this ranking, it is possible to immediately decide which meter needs immediate attention. This could mean recalibrating the instrument or the meter, or it could also mean replacement of this meter. So this measurement correction indicator that Sigmafine provides can be very helpful to find out where exactly the problem lies and which meters are faulty. Sigmafine has a carefully crafted execution methodology for deploying its material balance models. The first step is about defining the inputs. This involves the measurements, accuracy, and tolerance. The second stage involves audit and analysis of these measurements. Then we move on to the third stage, where the imbalance is evaluated. And the final stage is using the Sigmafine data reconciliation models to ensure that we receive reconciled data which will help to reduce the material imbalance in these refineries. So you may ask, why is material balance so important? What is the significance in industries around us? You will often notice that all data-centric processes and businesses keep generating tons of data. But this data is really worthless if it cannot be used in any decision making. The reconciled data from Sigmafine's material balance models ensures that the conditioned, refined, good quality data that we are receiving from the model can be used to provide insights into your business process, help to reduce costs, optimize processes, and even reduce energy emissions. This could also mean that this forms a platform for regulatory compliance. We cannot undermine the importance of good quality data. Data that can be accessed and is easily available across the enterprise. I'm sure you'll agree with me that the cost of poor quality data is often very high, resulting in errors and deviations from the expected outcome. The cost of fixing these errors is even more. Now, let us take a look at the case study.
In the following slides, we'll go through a case study for a refined products terminal where Emerson Measurement Consultancy and Primsoft Sigmafine worked together quite well to identify the measurement errors and supported the end user with the right solution. The diesel common storage and export facility comprises 7 flow metering systems from different production units, storage tanks, and export metering system. The inlet metering system is Coriolis-based system from a different manufacturer and were designed as a custody transfer system in accordance with the API standard. In situ proving facility was available and inferred mass proving was adopted. In inferred mass proving, the volume of the prover is multiplied by the flowing density from the online densiometer to calculate the prover mass, which is then compared against the Coriolis mass reading to calculate the meter factor, or in other words, the correction factor. The design uncertainty of the inlet meters was 0.25% at 95% confidence level, which is quite typical target for custody transfer measurement. The export metering system was believed to be operating correctly because after each loading, ship to shore figures were calculated and seemed to be within the expected range. As usual, each period, whether that is daily or monthly or both, the allocation team was calculating the imbalance figures, but with daily imbalance exceeding minus 2.5% and consistent imbalance bias. The imbalance figures seem to be quite disturbing because of the high financial exposure. The Sigmafine model could give the first indication that there is potentially a problem in the measurement across the facility, with the bias between the raw data and the reconciled data exceeds 2%. The model could even rank the meters based on their performance, which helped further with the investigation. As the export metering skid was believed to perform satisfactorily, measurement audit was conducted focusing on the inlet meters. The audit objective was to perform a gap analysis on the inlet meters to identify the root cause of the mass imbalance and recommend remedial actions as appropriate to rectify the identified gaps. From the initial discussions, it was also clear that something is wrong with the system because we could see that the performance of the meters during proving and between one proving to another is not within the expected and typical tolerance, which can be due to many reasons. And our goal was to identify the potential cause and recommend the required remedial actions. As in any engineering activities, the inspection always starts with the scope identification. Usually, the preliminary data we receive from site will be enough to identify the work scope. Once the scope is clear, we develop site-specific checklists, which are used during the survey. There are various metering standards. The correct standard for each application depends on the technology, contractual agreement, and the local regulatory requirements for that specific region. During the survey, there are main areas of interest for the inspector. These typically include measurement traceability, system design, and maintenance activities. In the generated report, findings are categorized based on their criticality, and high-level recommendations are given for a corrective action. For the proposed solution, the cost-benefit analysis is always considered to make sure that any system changes will be based on a well-informed decision and in line with the end user's financial goals. Consultancy services also extends after the project completion to make sure that the project goals are met. There are few common findings for liquid measurement that we have observed in many locations. Among those common observations is that the flow meter is not suitable for the specific application. It could be that the technology is not suitable for the fluid properties, like, for example, turbine meters for high viscosity oil, or the meter performance in terms of repeatability, reproducibility, is not as per the applicable standards and regulations. New meters with performance suitable for custody transfer application is recommended. The Emerson Elite Coriolis meters have been selected after thorough review with the end user. It's also quite common that we see debris and black powder in the pipeline for oil and gas applications. Black powder is produced as a result of chemical reaction or microbiologically influenced corrosion. Black powder affects the installed equipment and especially the isolation valves. Hence, a recommendation is usually made to install adequate filtration. This filtration will be upstream the system and the system equipment. A recommendation also is usually made to replace the isolation valves with another type that is less sensitive to the presence of debris. Also, in many cases, we see that the prover volume is just too small to achieve successful proving easily at the normal operating conditions. In such cases, a bigger proving volume, either by master meter or adequate volume prover size, is usually recommended. Human errors have been observed in many installations. Wrong flow computer constants or accepting wrong meter factors are really classical examples. Facility to control the flow computer constants and to consult the meter factor control chart and the meter factor acceptance tolerance before just accepting the new meter factor is always recommended. As you see from the mass balance trend, there is a significant improvement in the imbalance figures after the installation of the new meters, with the reduction of the monthly imbalance from minus 1.5% to around minus 0.5%. After implementing the recommendations, we see clearly that the bias between the raw data and the reconciled data almost diminished, and the Sigmafine data quality indicators are within the expected range.
After taking a look at what material balance is and the significance of implementing Sigmafine models to reduce this imbalance, let us look at the perspective of an integrated workflow. The data that's provided by Sigmafine material balance models is a refined and conditioned dataset. This can further be used for production accounting or to introduce new programs for controlling losses. Remember, losses is that element which is unidentified and often goes undetected. If you look at all these organizations and businesses that generates a lot of process data, they often get challenged with the 80-20 situation. This means most of their employees spend 80% of their time preparing and cleaning up data, and the remaining 20% is wasted in complaining about preparing this data. So just to highlight once again, the significance of error detection, detecting material imbalances at an early stage, and the importance of good quality data, I want to draw an analogy. Think about your favorite song. Now imagine you want to listen to this music right now. So you open up your music app, you punch in a keywords, and you start looking up for your music. You find that the search result is not great. Frustrated a bit, you decide to refine your search with a new set of keywords, maybe the singer or the language of the song. After a bit of struggle, you do see your music or your favorite song. You start playing it and then realize that the audio is of very poor quality. I'm sure this is going to impact your whole experience. Same is the case with poor quality data. I hope our presentation today inspires you to use Sigmafine models for material balance and data reconciliation. Now, I think it's time for us to take some question and answers from you.